Hi everyone, hope you're all keeping well. Now time for our next lesson. Today we're going to be looking at electrical circuits. So learning intention to explore the basics of electrical circuits, and success criteria: I can define what a conductor and insulator is. I can identify common electrical components and their circuit symbols. I can identify a series and parallel circuit. I know how to measure current and voltage in an electrical circuit. So conductors and insulators, we're obviously covering quite a lot here today, so I'm going to just kind of power through it. Some of it should be hopefully fairly simple to pick up. Other bits we'll probably need to chat through a wee bit, but don't worry too much. You can always ask questions at the end if you so desire. So conductors and insulators. Conductors are materials that allow electrical current to flow easily. Okay, so it allows the current to flow easily through it. Okay, so conductors tend to be things like metals. Generally, if you were asked to identify a material that what was likely to be a good conductor, I would suggest metal would be a good one. There are the odd exception. The odd exception to this. Graphite is a notable one. Graphite being a form of carbon, particularly you'll know this because it's the form of carbon in your pencil. So graphite is something that will allow electricity to flow through it easily as well. And that's obviously a non-metal. Carbon's not a metal, as I'm sure most of you probably already know. However, for the most part, non-metals tend not to conduct electricity easily, which leads us on to insulators, and that's what we call a material that doesn't allow electricity, this electrical current, to flow through it easily. And as I've just said, insulators tend to be non-metals. Okay, so we look at a wire. Okay, this is like a kind of cross section of a wire here, and so we have our kind of a protective coating around the outside, normally made of some kind of rubber or plastic kind of type material, and we have some sort of metal on the inside. And the reason for that is we obviously want the conductor around the outside. That's our insulator, around the outside I should say. We want our insulator around the outside. We don't want the conductor on the outside, we want the insulator on the outside. So some sort of material like rubber or plastic. And inside we want to make sure we've got that conductor. Something like copper. Gold's also a really, really good conductor, but obviously very, very expensive. So it doesn't tend to be kind of solid gold unless you've got a lot of money, I suppose. But you might find that you've got wiring at home potentially that maybe has gold plated, kind of gold plated conductor, which just means basically the surface of it is made of gold rather than the whole thing. Copper normally what you'd find inside a wire or a cable in your house, though. It tends to be quite a good conductor. So that's why a wire is kind of made like that. So I'm going to run through here really quickly. I'm not going to spend a huge amount of time on this slide. This slide basically got a lot of information that you'll be able to extract. Feel free to pause it to copy it down if you want. The PowerPoint will be available in Google Classroom as well, so you'll be able to access it on there if you just want to kind of pull the information straight from the PowerPoint. That's absolutely fine. I'll go through it row by row. I'm just not going to spend too much time. If you get a question about any of these after the fact, as I say, just ask questions in the comments afterwards. So first one here is a cell. Now cells are a really important one. We need to be really, really cautious with a cell. So you'll see here the picture for a cell. And this is basically what a cell looks like. This is what you would generally in everyday life call a battery, and actually what we would in everyday life we would call a battery is actually called a cell. This is the circuit symbol for a cell. So if we were building or we were designing a circuit, we would use this symbol in the circuit to define or to say that we wanted a cell there. And basically all a cell does is it converts chemical energy into electrical energy. Now, I should say there's going to be a number of pictures obviously coming down here. These pictures may be quite small, especially if you're viewing this on a mobile device. What I've done is on the next slide I've got bigger pictures of these, so don't worry if you can't really make out what's in the picture very easily. That's not a problem. There'll be some bigger pictures in the next slide for you to have a look at. So this is a cell here. So what's the difference between a cell and a battery? Why do we call that a battery when it's not really a battery? Well, a battery, this is an example of a battery here. This is a car battery actually. But the difference between a cell and a battery. Basically, a battery is two or more cells that are joined together. It's as simple as that. So if you connect the negative terminal of one cell to the positive terminal of another cell, then you've made yourself a battery. It's as simple as that. It's as easy as that. That's all we need to make a cell. To make a battery. If you have 3, you have 4, you can have 5, doesn't matter how many cells you add in there. As soon as you've got 2 or more joined together, you've got yourself a battery. Now this is quite convenient, because if you're asked to design a circuit or to show a circuit, you can do this one of 2 ways. So if you're asked to do a battery with 3 cells, you can either put in 3 of these, and you need to have the right number of them, because if it's asked for 3 cells, you've got to have 3 cells, and that's absolutely fine. I would be quite happy with that. The other thing you can do is you can put in, because it's asked for a battery of 3 cells, you can use this symbol here, and all this basically does, this is like having the first cell and the last cell, and then you've got these dots in the middle to represent all the cells in between. So that could be 2 cells, 3 cells, 4 cells, 5 cells, 100 cells, a million cells, doesn't really matter. This is just a battery. So if it asks for a battery, you can just put in one of these and that would be absolutely fine. A battery of 3 cells, of 4 cells, whatever. And obviously a battery will also convert chemical energy into electrical energy, as a cell does, because it's just made up of cells as well. This is a lamp, okay. Now quite often people will call it a bulb, which is technically wrong. The bulb is what goes in it. So if you look at the picture here, I'll show you this on the next slide as well. If you look at this here, the lamp is the whole thing here, the bulb is the bit which goes in it, okay? So we're actually looking at a lamp here. Now, a bulb actually has a different circuit symbol, which is why I'm saying it's technically wrong. So this circuit symbol is specifically for a lamp rather than a bulb. So don't call it a bulb. I know I'm saying bulb a lot here, but don't call it a bulb, call it a lamp, and you'll be absolutely fine. Lamps convert electrical energy into light energy. It's as simple as that. I'm going to come across a theme here where we're looking at these, the description of what they actually do, what these devices do. For the most part, we're going to look at them in terms of what they do in terms of the energy. So do they convert, for instance, the cell converting chemical energy into electrical energy, or the lamp converting that electrical energy then into light energy. We can look at the next one. We've got an ammeter here. Now this isn't going to convert any energy. This is an ammeter. Again, you'll see these pictures bigger. You see these pictures a little bit bigger in the next slide, so you don't need to worry if you can't see these too well here. This is the symbol for your ammeter, and it's used to measure current in a circuit, okay. Obviously you learned a little bit about current last time. This is a voltmeter. You can tell the difference between the two of these because one says A and one says V. And these can look like all sorts of different types of ones. So this is just an example of what they might look like. The ones we use in school actually are multimeters, so that they can do both and they can do other things as well. V is for a voltmeter, and this is just used to measure voltage. We'll talk more about voltage at a later stage, so don't worry too much about that just now. This is a resistor, so this is the symbol for a resistor. This is an example of what a resistor might look like. And basically the resistor, all a resistor does is it converts electrical energy into heat energy. Another easy one to remember there, it's just a conversion of energy. So electrical energy into heat energy. We'll talk a little bit about what a resistor does, because a resistor also kind of opposes the flow of current and kind of restricts it a little bit. So we'll talk more about that at a later stage. We'll not go into that in too much detail just now. For now, all you need to know is that the resistor converts that electrical energy into heat energy. Finally, this is a switch. Now, if you're viewing this on a mobile device, you'll not be able to see any of these, and I doubt you'll be able to make any of these out clearly. So don't worry. On the next slide again, I've got this picture a bit bigger. This is the symbol. So you see the wee gap here. So there's a gap here. Basically, the circuit isn't complete, so it won't. The current can't flow. So you need to close this gap for the current to flow, and that's how the switch works. So you close the switch and the current can flow. Basically, so it starts or stops the current from flowing around the circuit. So here's these bigger pictures I kept promising you. So we've got the cell, the battery. Now I've used this battery here because this is a kind of car battery. It's something which I'm sure some of you at least will be somewhat familiar with. You'll maybe have seen one at some point in your lives. We could very well have just had 2 of these joined together with a wire. That would have been absolutely fine as well, or 3 or 4 of them with a wire. That would be absolutely fine. This is a lamp, so this is kind of similar to what the kind of types of lamps that we sometimes use in school. We've got a resistor. Quite often we would have them mounted with little terminals we can put our wires into. A ammeter or voltmeter here, and these are just a sample of some different switches. So you've got some kind of push switches and ones that will actually kind of click over, and ones you'll need to hold for them to kind of keep doing their job, and so on and so forth. Loads and loads of different switches, but they all do the same thing. They all start or stop that current from flowing in the circuit. So a series circuit. This is an example of a series circuit here. And the way a series circuit works is the current has to flow around the circuit through each of these components one at a time. Okay, so remember, current is just that flow of electrons, a flow of charge. So if we have our electron here, it's going to travel around the circuit. It's going to go through each of these one at a time, and it's going to end up back at the battery here. Okay, so we saw that there, just went through each one of these components one after the other, and that's the important thing about a series circuit. The charge has to flow through each of these components one after the other. It can't kind of a flow through the two at the same time, or you can't go through the first one, then skip the second one and go to the third one, and then come back to this one. It's got to just go through them one after the other. So it's like it's like a circuit. You know, if you're going around the circuit, outside the science block, out the kind of back of the science block, where most of you were doing PE before we went into lockdown. If you want to go around that, obviously technically we could cut across the grass, but what you're meant to do is you're meant to go round the track. You're not meant to kind of take shortcuts across it, so you just kind of go round that circuit. So a little note there, in a series circuit the current flows through each component one after the other. It's as simple as that. So parallel circuits, well, this is an example of a parallel circuit here, a little bit different. So we've got our wire comes down round to here, and it comes into here, and then it also comes down to here. So you can already see, hopefully, that there's going to be an issue here. If our electron comes down here, which path does it choose? Does it go this way? Does it go this way? Well, what basically happens is it will go both ways. Obviously, we've got more than one electron. That last animation we looked at just had that one electron which went round. Obviously, you've got this continuous flow of electrons around the circuit, which is what gives us our current. So what basically happens here is an electron comes round here, and one will go one way, one will go another way, and then some will go one way, some will go the other way. And how many go each way depends on what components you've got in each one. That's going to get into some quite complicated physics at that point. We'll probably look at that more when we look at the kind of National 5 content rather than what we're looking at just now. So just a quick look at that then. So we've got an electron here, and it's going to travel round. It's going to reach this branch here. It can go either way. So this one's going to go along here. We'll introduce another one. It's going to reach this branch, and instead of going the same way, it's going to go the other way. So it's going to go through there. They both come round to this side, and then they'll travel back towards the battery before going back through the battery again to pick up some more energy. And that's exactly what happens. You just have this continuous flow with some going this way and some going down here. It's a bit like I kind of tend to think of it as a river that kind of branches off into two kind of rivers. And some of the water is going to go one way, some of the water is going to go the other way. And if the river then joined up later on again, then you would both go back into the same river here. And that's just the way I've always tended to think of this. So in a parallel circuit, the current splits and can flow along more than one. And I've used the word branch here. So what we do is we call each of these a branch. So each of these paths that it can take, we call a branch. So this is a branch, and this is a branch. This might be branch 1, this might be branch 2. Depends on how you want to define it. It's not that important, and quite often you can get to define these yourself, which is quite nice. You get to, if you'd rather the bottom one with branch 1, you could define it as that. That's not an issue, unless it's given to you, of course, in the question. If you're asked a question at some point about this. So that's parallel circuit. Measuring current. Okay, now I'm aware that I'm kind of just powering through, blasting a whole load of information at you here. don't worry, you can go through and watch this video a couple of times. I kind of figured I was well getting through the content, and you can go back and watch it if necessary. If you find that you're going through it and your head's kind of getting a wee bit scrambled, stop after maybe this point. Maybe want to pause just now, and then kind of just kind of take a few minutes to kind of assimilate what you've just kind of just seen, and then kind of continue on from this point. Or you can just continue on if that's what you want to do. So measuring current, how do we measure current? Well, here we've got a circuit. Again, we've got a battery here, and we've got two lamps. Okay, a nice simple circuit. So a battery and two lamps. If I want to measure the current in this circuit, all I need to do is put an ammeter in series with my components. So I add my ammeter in here. Now I can add it in there. I could also add it in here. I could add it in there. Doesn't matter where I add it in. That will measure my current anywhere in that circuit. We'll come back and have a look at current in series and parallel circuits in a separate lesson, but we can put that ammeter in anywhere, and that will give us a value for the current at those points in the circuit. So it's as simple as that. So to measure the current, the ammeter is always placed in series with the other components. Okay, so it's going to be placed in series. Now what this does mean is that you're going to have to break the circuit to add the ammeter in. So what that means is, obviously we had a wire which came round, only came all the way, so just one wire went from here back to the battery. We've had to unplug that from the battery and plug it into the ammeter. Then we have to get another wire and plug it into the other side of the ammeter and have that coming back round to the battery. If I can get a hold of some equipment, guys, if I'm in school at some point, I'll maybe see if I can grab some equipment and bring it back, and I can do some wee demonstrations, wee kind of demonstration videos of how this is actually done using real equipment. Unfortunately, I don't have anything here to actually show you that with at the minute. But I can kind of show you how to kind of construct it, so hopefully when we do get back into school and we're able to do experiments again, this isn't going to be completely unheard of for you. So yeah, that's how to measure current. Measuring voltage, on the other hand, we've got our well, it's the same circuit. So we've got a battery here, we've got our two lamps. Now you'd be forgiven for thinking you might want to put your voltmeter in there, but that is absolutely wrong. Don't ever do this, okay? If you do that, it's wrong. It's not going to give you a reading. It's not really going to do anything to the voltmeter. It might give you a reading, it might not, but it's not going to be the reading that you're looking for. And if you do it in a test or an exam or something, then you're asked to design a circuit and you put your voltmeter in there, you would just lose marks. That's how that's going to work. So we don't want to do that, so let's remove that from there. So if we want to measure our voltage, what we do is we put it across our components, okay? So what we do is we take a one lead coming from one side of the battery, and that goes into the voltmeter, one lead from the other side of the battery into a voltmeter, and that'll give us the voltage across the battery. Now we always say the voltage is across and the current is through, okay? And we say the voltage is across because it is just across. That's what we're looking at. We're looking at this voltage across the battery here. We could do the same down here. We could do the voltage across this first lamp here. So we could put the voltage across this first lamp here, that'd be brilliant. We can put the voltage across this second lamp here, that's absolutely fine as well. So to measure the voltage, the voltmeter is always placed across the component or components, because I put this in brackets here, the VS, because what we could do is we could put the voltmeter across both of these. So we had one lead coming from here to the voltmeter and the other one from the other side of the voltmeter going all the way along here and down to the other side of this lamp. We just going to skip this line here. Then that would give us the voltage across both these lamps at the same time, which sometimes can be quite handy. Good thing about this is we do not need to break this circuit. Okay, so all you need to do is plug in your lead into either side of your lamp, and it will tell you your voltage, or of course either side of your battery, depending on which component you are measuring the voltage on. Okay, so that's all I'm going to go over today. I've got a number of tasks for you to do. They're in the video here. You'll be able to pause the video and look at them here, or you can go away and look at the PowerPoint. They're in the PowerPoint, which is on Google Classroom, or on the website, depending on where you're watching this. So I want you to design a number of circuits. So when I say design, that's just basically draw them. Now I'm going to give you a couple of rules for this. You can do this in your jotter, or you can do it in a Google Doc. I'm going to get you to submit these but we'll go through that at a later stage. We'll talk about that later. So when you're drawing a circuit, you'll notice from all the diagrams I've done, the leads are always drawn with straight lines and normally right angles wherever possible as well between them. That's how I expect you to draw all your circuit diagrams. It's done like that, and it's a good habit to get into, because the circuits we're looking at tend to be fairly simple, but if you are trying to draw a much more complicated diagram, it gets very, very hard to follow where those wires are going if you've just got these squiggly lines going all over the place. So that's why we always use straight lines. So use a ruler. I expect you to be using a ruler to do this. If you don't have a ruler, do it in the Google Doc. You can do straight lines nice and easily in a Google Doc. You'll be able to put in the components. There should be some shapes in there as well, which will be able to help you do the various components. And as a little cheat, you can always then copy and paste. Once you've done one lamp, you can copy and paste that and just put that in for a second lamp if you need it, or put it in for a second circuit, because if you've drawn it once there, then there's no need to draw it a second time. So 4 circuits here. The first 3 are series circuits. So the first one is a circuit with a cell and a lamp in series. The second one is a circuit with a battery and 2 lamps in series. The third one is a battery made from 3 cells, 2 lamps and a resistor in series. The fourth one is a parallel circuit. That's going to have 4 cells, which will be in series, so that'll be 4 cells in series. So they'll just kind of be right next to each other on the diagram. I thought we'll give you that just to be nice. We don't want to make life too difficult for you. A lamp and a resistor in the first branch, and 2 lamps in the second branch. So that one's a little bit more complicated, okay? So if you're struggling with that, go back and have a look at some of the diagrams and see if you can figure out what we mean by it. I'll just remind you, that's in, I've kind of written it down at the bottom here, but remember that your leads, or the wires connecting the components, must be straight lines, okay? That's what I'm going to expect from you here. Okay, once you've done these, there are some questions for you to answer as well. So I've got 3 questions here. Here's the first one. Answer them either in the same Google Doc that you've already started, or if you do them in your jotter, you can kind of take pictures and you can upload them or whatever. In fact, actually, you'd be better doing them in a Google Doc and then maybe adding the pictures into the Google Doc, but we'll talk about that in a wee minute. So question here, what do you think would happen if to the other bulb if one of these were unscrewed? Okay, so one of these bulbs were unscrewed. I'm using bulb quite specifically here because this is obviously a lamp. If we unscrew the bulb from one of these lamps, what would happen to the other light? Would it stay lit up? Would it go out? Would it get dimmer? Would it get brighter? What do you think is going to happen? So if you unscrew one of these bulbs from its lamp, what's going to happen to the other one? Same question, but this time we've got a parallel circuit, okay? And just to be clear, if you see a switch, we presume the switch is closed, okay? So don't worry about the switch in there. If the switch is presume the switch is closed and both bulbs are on, if you unscrew one of these bulbs from its lamp, what will happen to the other one? What do you think is going to happen to the other one? And finally, third question, can you think of an advantage of a parallel circuit? And maybe think about your answers for those 2 questions. Can you think of an advantage of a parallel circuit over a series circuit? I'll give you a little clue here. I put some switches in just to maybe give you a little hint as to what might be the answer there. Might help, might not help, don't worry. If the switches don't help, don't worry about that. But if you can think of an advantage, that would be absolutely brilliant. And what I'll do is I'll get you to submit these in the Google Doc on Google Classroom afterwards, but there'll be instructions on Google Classroom for that. So that's us. Success criteria. We'll just run through this one last time. I can define what a conductor and insulator are. I can identify common electrical components and their circuit symbols. I can identify a series and parallel circuit. I know how to measure current and voltage in an electrical circuit. Right, that's us then for today, guys. Remember, go away and answer these questions now if you've not done so already. If you've paused it and gone along as we're going along, that's brilliant. If you've not, remember you can access the PowerPoint either from Google Classroom or from the website, depending on where you're viewing the video just now. And that's basically us for today. So I'll see you again next time. Keep yourself safe